Hello everyone, Dr. Young here, and in this video I'm going to talk to you about some of the common reactions of carboxylic acids. And we'll put this into a little more context with all of the carboxylic acid derivatives and look at a couple of practice problems here. So first, remember that you can form carboxylic acids in a variety of ways. I had a previous video about, you can oxidize them from alcohols, you can do ozonolysis of alkynes, you can do oxidative cleavage of alkenes, you can use Grignard reaction and expose it to carbon dioxide, you can do cyanide hydrolysis. There's all kinds of different ways to make carboxylic acids. One of the important things to remember about carboxylic acids, is that obviously they are acidic, hence the name. So that means that they're going to lose that H, in normal solutions. If you have just water, all your carboxylic acids are going to lose their H's because of the pKa's, and that should be, P capital K A. pKa's are around 5. So if you have just like a regular old acetic acid, I think the pK is like 4.76, 4.75, something like that. Right? It's about 5. It's about 5. But if you take a look at like different acids, I just want to put this in a little more context for you here. So I highlighted here, and I'll just call these A, B, C. Right? So A, B, C, D, E. If you look at all these conjugates, for A, you've got double bond O, O minus. I'll draw lone pairs so I can emphasize something in a sec. Another O minus on this sucker. For this one, same thing. And should have just drawn out all these conjugates so I could not waste your time, but I'll waste your time anyways. Right, so I'm going to look at all of these different conjugates here. So the trifluoroacetic acid is the last one here. And when you're asking, how acidic are these things, what you're really asking, is how how stable is their conjugate base, The more stable the conjugate base is, the easier it is to lose that H. So for, again, regular carboxylic acids, they just lose their hydrogen in water, because the pH of water is around 7, right? And if you're trying to compare these to one another, we just want to ask ourselves, how stable are these? So right off the bat, one of them should jump out as the least stable, and that would be this one over here on the right, D, because this one has no delocalization, no electron delocalization. All the rest of them have some amount of delocalization, so they're all inherently going to be more stable. They're all negative oxygens, so if you have one negative oxygen that is not spread out, probably going to be less stable than the ones that are spread out. Because all of these other ones, you're spreading out that charge on another O, So the first one, you can delocalize into one carbonyl, or you could actually, for this one, you could have delocalized into the other carbonyl, so you have 2 resonance structures that I need to draw. If I look at just the plain old acetic acid here, that has a delocalization. The fluoroacetic acid has delocalization, and the trifluoroacetic acid has delocalization. And so another thing should jump out, that A has the most, has the most delocalization. So this should be the most stable. And I'll put for the other one, the one that has no delocalization, that's going to be the least stable. It's going to be the highest energy anion. So right off the bat, I think that A is going to be my most acidic, D over here is going to be my least acidic. So I've got 5 things, so I'll call that number 5. Now between B, C, and E, they're all really similar in that they all have one resonance structure. I'm not drawing them, but it just be put the negative on the other O and the carbonyl on the right-hand side. And then we've got these fluorines here. That's one difference, B has no fluorines, C has 1 fluorine, E has 3 fluorines. Fluorines being really electronegative are going to withdraw electron density, So these are all going to withdraw electron density. And we just have to decide, is withdrawing electron density, through the inductive effect, is that going to help stabilize an anion or hurt an anion? And if you remember that anions are unstable because they have too many electrons, they're negative, then helping to spread out that negative charge is going to stabilize it and lower the energy. So if these fluorines are going to help here. And you can imagine that if you have 3 fluorines, that's going to help the most. 1 fluorine will help some, 3 fluorines will help more. So next we have the 3 fluorines are going to, so I'll say 3 fluorine atoms are are, I'll say, spreading out the negative charge there. All right, they're pulling electrons away. So of the three of these, the one on the right, E, is going to be your second most acidic one because it has three of those helping groups, three of those fluorines. That would put C as my third best and B as my fourth best. And to give you an idea with these pKa's, things like trifluoroacetic acid, this thing has a pKa of like 0.2. So 0.2, so almost zero. So almost 5 pKa units less than without the fluorines, which is pretty significant. And then when you look at these sulfonic acids like A, they tend to be negative. They're really low. Just to give you an idea. So you just want to keep in mind that carboxylic acids are in fact acids, and you need to watch out if you have anything basic at all, amines, hydroxides, stuff like that, you're just gonna do an acid-base reaction. And so this actually limits the type of reactions that carboxylic acids can do because any kind of decent nucleophile is probably gonna do an acid-base reaction with it, halides aside. So let's talk more about that. Remember I put this up in a video earlier when I was talking about the general reactivity of your carboxylic acid derivatives. That one was a hand version. Here it is, just boom, all at once. Right, and just real quick, reminding you that we can take our carboxylic acids and turn them into these acyl halides, which we said were really, really reactive, right? Remember we have these in order of most to least reactive. So most reactive to least reactive. Right? Nitriles are hard to hydrolyze. You have to really, really heat them up to get them to work. Versus acyl halides, they hydrolyze if they even just sniff water. You just got to be really careful. If there's just water around, they're going to hydrolyze immediately. And so what we're saying is that if I wanted to turn like let's say I wanted to turn an ester into, so let's say I wanted to start with an ester. And I wanted to finish, I wanted to turn it into an acyl halide for some reason. The idea is that I cannot just like directly go up this ladder, right? I can't do this. What I have to do instead is I have to take the ester, I have to hydrolyze it using one of those two methods, either the acid catalyzed or base mediated, to turn into the carboxylic acid and then go from the carboxylic acid over to the acyl halide using SOCO2 or PBr3, right? So I can't move directly up this, I have to move through hydrolysis, through the carboxylic acid, and go back up that way. And then I can move down from acyl halide into anything I want. You just add the thing you want. But we'll talk more about that when we talk about acyl halides. But so we want to try to figure out, right, how do we get carboxylic acids into these other derivatives? Also recall that in a previous video, I mentioned that the general addition-elimination reaction doesn't really work so well with carboxylic acids, generally speaking here, right? So if I have some generic carboxylic acid, let's say we have benzoic acid here, that's a pH. And I want to turn it into like an amide, for example. Let's say I want to turn it to the dimethyl, the NN-dimethyl amide. The problem here is that if you're trying to mix these together, right, you can't just have your negative go and attack that partially positive carbon here, right? Partial negative, partial positive, partial negative. It's not going to work that way because what you're going to see instead is that you're going to do an acid-base reaction, right? So if I have, again, that benzoic acid here, again, I'm going to add that diethylamine. What you're going to see instead is that you just do an acid-base reaction. Because you have an amine, which is basic, you have a carboxylic acid, which is acidic, and so your first equivalent of amine is simply going to deprotonate your carboxylic acid, and all you're going to end up with is this ammonium salt. And that's not so great. And then as soon as you make your carboxylate, that thing is a terrible electrophile. I'll even write terrible. This is a terrible electrophile, right? You have a full-on negative on that oxygen. That's a very, very electron-rich carbonyl. So it becomes an extremely bad electrophile that we can't do too much with unless we want to make little bombs and increase the pressure like crazy, which generally is not the greenest thing to do or the safest thing to do. So what we do is we usually convert to an acyl halide first and then add whatever nucleophile we want. So for example, if I wanted to turn that benzoic acid into that amide, right? Like I was wanting to turn that benzoic acid into this amide. What I would do first is I would just add SlCl2 and some base like triethylamine or pyridine or something like that. And that would turn it into the acyl halide. Which is awesome because these are super reactive. They will react with any good or poor nucleophile. It'll just add. And so then if I want to make that diethylamine, all I have to do here is I just need to add the diethylamine. That will react no problem, right? Notice that the acyl halide doesn't have that acidic OH anymore. It doesn't have the acidic H. So I don't have to worry about an acid-base reaction. I can just go ahead and add my diethylamine, and it's going to go ahead and do that addition elimination step. And then I can get my amide. So it's much more straightforward, much easier to do. Usually when you do this step, though, you have to add 2 equivalents of amine because one's going to be used as a base scavenger at the end because, again, amines are fairly basic. All right, just to give you a quick idea of the mechanism, we'll do more of this later when we talk about acyl halides, but the idea here, here's the quick cheaters version. Don't put these together like I am. But right, you would attack that partially positive carbon, the electrons would kick up, those electrons would then kick down and kick out your chloride to give you this, but you'd end up losing this hydrogen, right? This hydrogen would go off, become H+, but that H+ would get picked up by, like I was saying, that second equivalent of amine. But either way, I'm able to make my amide. And I'm able to make that amide, not directly from the carboxylic acid, but by going through the acyl halide. And we're going to see that theme a lot. It's really a fast, easy, quick way to make things like amides and esters and stuff like that. Now, there are some reactions that we need to come back to. We've already learned about lithium aluminum hydride before we used it to reduce ketones and aldehydes. And now we're going to look at it to reduce any of the carboxylic acid derivatives, really. So this video is about carboxylic acids, so let's do the carboxylic acids. Right, so the idea here is that if you have a carboxylic acid, and let's say we have a ketone on here too, just to kind of show both to remind you. If you add lithium aluminum hydride, and again, you may see something like THF or diethyl ether as the solvent. You may not, that's fine. But if you see one of these polar aprotic solvents, just roll with it. And then you need some sort of acid workup. This can be water or an acid. And this is just to protonate the O- that you're going to have, right? So it can be water or some sort of acid, and whatever acid you want. And the idea here is, right, you want to remember that we said that lithium aluminum hydride, it actually donates roughly, it's 3 point something, but roughly 3 equivalents, a little more than 3 equivalents of hydride. So it's actually able to fully reduce something all the way down to having just 1 bond to something more electronegative. So what that means is that while over here on the left-hand side, we have 3 CO bonds, and here we have 2 CO bonds. In the end, and I'll label these carbons 1, 2, 3, 4, and 5. In the end, both of them are going to be brought down to just alcohols. Right, again, so where this is carbon 1, 2, 3, 4, and 5, both of them are going to be reduced down to just 1 OH here, 1 OH here. Because these hydrides, right, so these hydrides here, again, there's 4 of them on there, but really a little more than 3 on average are available to be donated. Those hydrides, you end up putting 2 on carbon 1, and we got 1 on carbon 4. And so the mechanism of reducing that ketone is exactly what I showed you before. You can look it up online or in your book. And then the mechanism for the carboxylic acid reduction is really similar, but a little different because you've got a second step is the idea. So let me show you that mechanism real quick. I'm going to use a simpler carboxylic acid here. So step 1, right, you have your LAH, lithium aluminum hydride. Step 2, some sort of acid workup. So you've got your Al, your aluminum hydride, and there's some lithium floating around. The first step of this, I don't know if you remember this, first step of this, right, we said that the LAH was actually, the LAH is actually a little basic. And so you have to watch out for this hydride. The first thing that's going to happen with this hydride is it's going to deprotonate your carboxylic acid just like any other good base would. It's going to deprotonate your carboxylic acid. And what's going to happen, and what makes these reductions a little bit dangerous, you have to pay attention to them, is that the first thing you form, right, so yes, I have an O minus, but I also created HH, right, or in other words, hydrogen gas. And the problem with hydrogen gas is that it's super flammable. And so you're generating this flammable hydrogen gas that bubbles out of your reaction. Hopefully you're doing this in a hood. But also the reaction is exothermic, so it gets real hot and you start producing a bunch of hydrogen. So you really want to be careful when you're doing these so you don't like blow anything up or get a big old fireball in your hood. They behave all right. You just have to really, pay attention to what you're doing. This is the point. Now you lost one of your hydrides from your lithium aluminum hydride. So now you just have aluminum with 3 hydrogens on it. And so that O minus is able to add back in, whoops, I don't need that tool. Not highlighting anything. Will you go back, my friend? Come on. And I'll erase you. Oh, there you go. So what you're going to have happen here, now that's too far, is that the negative on this oxygen can add back into your aluminum, right? It lacks an octet. That oxygen's full of electrons. So those two things are going to add together. Just do a Lewis acid-base reaction. And what that does is that puts the negative back on that aluminum. So now we've got another upset, in a way, aluminum. It's negative. It's also able to spit out a second hydride. And so now it's going to spit out that second hydride to the carbonyl that we have, partial negative, partial positive. We're going to spit that hydride out, and I'll just draw it from here so that it attacks your carbonyl. So we've added a hydride. We have this O aluminum thing, just 2 hydrogens now. These electrons can drop back down and kick out this to give us an amide, and then an aluminum double bonded to an oxygen with a hydride and a hydride. Now, whether or not, there's a little debate about the mechanism of this. Whether or not it's this hydride species, it may not be, because that minus is so much more stabilized now that it has an oxygen on there, right? Oxygen's still electronegative. It's going to stabilize that negative charge. Whether or not it's that aluminum species that I drew or a fresh aluminum tetrahydride that comes along to donate the hydrogen, either way, this aldehyde gets reduced, right? So I'm not going to care which one you pick. I'm not sure that folks are 100% sure on which one it is, because it's kind of hard to tell. It's a big gray mess that you're trying to analyze that's hot and flammable. But one of these hydrides attacks the carbonyl again. I'll draw this a little bit better. Because again, you have a partial negative, partial positive. And that's going to get you to your almost product, where you have an O minus and an H and an H. And then, like we said, the last step, step 2 here, is that you just add an H plus somehow, somewhere, so that you protonate your product to get your product. Right? And like I showed you up in that top one, you ended up adding 2 hydrogens, right? You added 2 hydrides. This hydride and this hydride both came from the LAH, right? Both of those came from the LAH. So you're able to add 2 H's there. You've reduced your carboxylic acid down to the alcohol. And we're going to see a similar mechanism for reducing esters and other carboxylic acid derivatives. Now, one reaction that the carboxylic acids do, and it's a classical one, it's a Fischer one. Fischer's a real famous chemist, known a lot for his carboxylic or as a carbohydrate chemistry. But you're going to hear Fischer esterification, so I'm going to show it to you, even though I don't like it, and I don't think people actually do it. They would go SOCl2 and just add the alcohol instead. But I need to show this to you. And so generically, right, you're going to have a carboxylic acid. You're going to have some carboxylic acid. You're going to have an alcohol. So you're gonna see some ROH, some alcohol, and you're gonna see an acid catalyst. So there's gonna be some sort of H plus, some catalytic amount. It'll either write catalytic or maybe like 5%, 1%, something like that, or maybe just an acid. And what you're gonna get in the end, right? Since this is an esterification, what you're gonna get at the end is an ester, where whatever this alcohol was, and I'll put R prime to show that it's different. Whatever that alcohol is, that's what's going to be the R group on this new ester. And then you're going to make water plus water. This is a condensation reaction. So this Fischer esterification, you'll spot it by because you're going to have a carboxylic acid, you're going to have an alcohol, some sort of acid, and basically you're going to just slap that R group, replace it where the H was. So I have an example down here. So I've got my carboxylic acid, looks like I've got ethanol, I've got catalytic amount of sulfuric acid. So to draw this, I'm just going to write that it's still the benzoic acid, O, and now ET, and then plus water. Whether or not you write water, I don't really care. Technically it's there, but I'm an organic chemist, so I just care about the carbons. So I just care that you showed me that, right? And so I made my ester. The mechanism is kind of gnarly, but I'm going to show it to you because it's a twofer for me, because we'll talk about the hydrolysis of an ester is the exact same reaction but backwards. So let me show you. I'll do the reaction that's just right here above. So let's do benzoic acid here. And it's the mechanism, right? So I'm going to show all of the electrons and all of the arrows and all of the formal charges. And I've got H plus, HSO4 minus, right? So I went ahead and I split up my strong acid because it's a strong acid, right? So H plus, HSO4 minus. Now, if I look at my carboxylic acid, I've got some, partial negative, partial positive, etc. And the most reactive thing probably is going to be the largest charge, which is on my H plus. I know I have an SO4 minus, but remember that minus is super stabilized because it's delocalized. So it's not really a good nucleophile. It's not a good base. It's just going to be pretty much a spectator ion. And anytime I have acid and carbonyl compounds, almost always that first step, right, is to protonate the carbonyl, which is exactly what we're going to do here. So we're going to protonate that carbonyl. This puts a positive charge on the carbonyl, which again just makes it more electrophilic, right? It makes it more electrophilic, which is good because now my poor nucleophile, my ethanol, can add in to that carbonyl. Those electrons kick up to form this bizarre species. So I've got an OH. The ethanol just added in, and I had an OH that was there already. Now, anytime we have a positive oxygen with a hydrogen on it, right, we want to remember that oxygen's not thrilled about being positive, so it can take electrons back from something. It might be that CO bond that it just made. That's why I can go backwards, so I do that reversible arrow. Or it could be that the hydrogen gets kicked off, right? The electrons go back to the oxygen there, leaving an H plus. That will move me forward, so let's see what that does. If I have that, I have all of these alcohols, and I have this ethyl ether, and I have H+. Now, all of these oxygens, I'm not drawing all the partial charges on everything, but all these oxygens are partially negative, right? They're the only negative things on here. So that H+ is probably attracted to one of those oxygens. Now, I could put the H+ back on the ethyl ether, make it that ethanol piece down at the bottom. That's going backwards. Again, that's why I drew a reversible arrow, because I could go backwards. Or let's see what happens if I add it to one of the alcohol groups. What if one of those gets protonated instead? That's a different species. So I'm left with this. Now, again, we have another situation where we have oxygen where it's positive. And so, again, it can either take electrons back. It's going to take electrons back from something. It could just kick that H back off, which is going backwards. So this is a reversible step also. Or if you take a look at this, this is like a water leaving group, right? And we said that water is very stable when it leaves. The question is, how stable would be the cation we leave behind, right? Because we're going to leave a positive on a cation. And in this case, it's going to be very stable. And I'm going to draw this separately. You might see mechanisms drawn out where this is slightly different, but I'm going to draw these separately just so we can really see it. If these leave, we're actually going to form a nice resonance stabilized carbocation here. Not only, well, in this case, not only is it near the aromatic ring, that phenyl group, but you have lone pairs above and below it, right? So plus and the O-ethyl group down here, right? Plus water. Right, what I'm saying is I can have these electrons drop down, and this is just a resonance structure. It's the same molecule. This is just a resonance structure. Let me see if I can get this all in here. So that makes that carbocation relatively stable, right? You might look at it first and be like, oh man, that's just a primary carbocation, but it's actually resonance stabilized by the lone pair up top. And actually, I should have drawn a third one. Imagine a third one. I don't have space here. Imagine a third one, though, where the lone pair, and I'll draw this in red just to kind of, or I'll draw it in green just to kind of show it. You could have had the lone pair from the bottom one drop down and get a similar and analogous resonance structure. So you actually have 3 resonance contributors here. So you're spreading out that positive charge over 3 atoms. Plus, you're able to fill that empty octet that would be on the carbon, which again stabilizes that cation a lot. What is interesting here, though, is that we're actually really close to the very end. Because again, if you look up top, the one that I drew last here, I have a it looks like a protonated carbonyl, right? I have a double bond O with an H on it. Again, we said that's not super stable. And so if that H gets kicked off and that carbonyl gets its lone pair back, that is the ester. So pH, double bond O, O, ET. That is the ester that we were trying to make. Plus, I regenerated my acid catalyst. And I'm going to put this as reversible because if I added the acid catalyst, right, the acid could reprotonate the carbonyl, and then we'd start going backwards. But that's how we would get to the product, right? It's a pretty long mechanism, but there's not too many crazy steps. It's just a lot of proton transfers, basically. Now, what I don't like about the Fischer esterification, first of all, it's cool that he discovered it. I'm not trying to talk crap about that, but it doesn't have a great yield because all of these things are in equilibrium. Right? If you take a look at this, you can just go backwards. And so you don't end up getting like 100% yield on these things typically, right? They're like 50-50-ish, give or take, depending on what the alcohol is. And so what you do to drive this reaction forward is you just try to take advantage of Le Chatelier's principle. And that means you either remove water the whole time, right? Since you form water down here, you form water here. If you remove this water, right, by like trying to boil it away, you can get rid of that water. You're just through Le Chatelier's principle, you're going to drive the reaction forward and get more product, right? Since water's on the products, water's on the product side. That's one way to get these reactions to have higher yields. The other way is to add a huge excess of the ethanol. Because if you have a huge excess of ethanol, again, Le Chatelier, you have a ton of starting materials, that's going to drive the equilibrium to the right, and so that, again, that'll increase your yield. In this case, I'm just using ethanol. Not a big deal to use a lot of ethanol, but maybe this was a fancier alcohol that I spent a while making and I didn't want to just waste a bunch. Didn't want to like do it in a use it as a solvent. This would not be the best way to do this reaction. It's much easier and faster and takes less energy to just take your benzoic acid in this case, add some SOCl2 or oxalochloride or something like that, turn it into the acyl halide, drip some ethanol into it. By the time you take your first TLC or something, you're done. Reaction's done. No big deal. Much easier, much less time, much less heat. But anyways, this is the Fischer esterification. And what I want to mention here, I'll do this in purple, the reverse of this, if you do exactly the reverse of this, this is the acid catalyzed hydrolysis. Of an ester. It's this exact reaction, you just go backwards. That's it. So 2 mechanisms in one. Now for some examples here, let's start off with this top one. This is screaming, well, you know, again, this is the part where you should probably pause, see what you can do with these. So I'll wait a sec. Go ahead and hit pause. No, really. So if I look at this, this is screaming the Fischer esterification to me because I have a carboxylic acid, I have an alcohol, and I have a acid. So all I'm going to do is I'm going to take this, well, let's see, how many carbons is it? 1, 2, 3, 4, 4 carbon alcohol. So I'm just going to redraw my carboxylic acid, which was this, and add a 4 carbon piece. 1, 2, 3, 4. Boom, done. Right, so now this piece right here, those 4 pieces, that's these 4 pieces, and then plus water. Sodium borohydride, I just brought this back, right? This was the old reagent. We said that this was the weaker of the two, and we said it could only reduce aldehydes and ketones. It cannot oxidize any of the carboxylic acids or its derivatives. And since this is a carboxylic acid, this reaction is going to be a big fat no reaction. Nothing's going to happen here. Sodium borohydride is not going to really do much with the carboxylic acid. It's not going to reduce it down to an alcohol. Now down here we do have the LAH, right? This was the stronger one that can reduce anything. Right? It can reduce all the carboxylic acid derivatives and the aldehydes and ketones. And so I'm just going to draw, again, my skeleton backbone, and wherever I had this, so carbon 1, 2, 3, and 4, 1, 2, 3, and 4, I'm just going to put alcohols where the carboxylic acids were. And it doesn't matter if your OH is sticking up or to the right or whatever on carbon 1, it just needs to be an alcohol. So right, it would just reduce them both, or reduces them both. And then lastly, for this one, here's just a little synthesis problem here. We're like, well, how did I get from that to that? It's going to take multiple steps. It's not just one reagent. But I do see, right, I do see that there's an ester here. So I know I have to do some sort of esterification, whether it's the Fischer one, or I go do SOCl2 and add the alcohol. And I do see that I added a carbon. Right, this is a new carbon. That wasn't there before. There's only 1 carbon coming off that benzene ring. Now there's 2 carbons coming off that benzene ring. So that means I need to use either the Grignard or the cyanide thing and then hydrolyze it to get a carboxylic acid. I'm going to go with the cyanide thing. So step 1, NaCN. Step 2, acid and heat. That should give me this. And if that doesn't sound familiar, go look back at that formation of carboxylic acids video. And then from here, if I want to do the Fischer synthesis like I did up above, I would just take that isopropanol and I'd add some sort of acid catalyst. And then probably heat the bejesus out of this. Or like I said, and I'll talk more about this in future videos, or it'd be a lot faster to do step 1, SOCl2, and step 2, all you need to do is just add the isopropanol and it's going to react like immediately and you'll be done. And then you go home. Anyways, I hope that these are enough examples to start getting you going. Do lots and lots of practice. Happy studying. Take care.